Hey, good morning, everybody. So today we're going to get into the amino acids chapter and start talking about some of that. Now, I've skipped lipids and I've skipped carbohydrates, in part because I don't much care to talk about them. But we have sprinkled in those topics throughout the semesters. We've talked about fatty acids when we talked in Chapter 10 about free radical oxidation and the formation of prostaglandins, for example, through the arachidonic acid, and how ibuprofen gets into the enzyme active site and stops that from happening. So we've talked about a variety of those types of things. We talked about sugars when we talked about the Tollens test, right? So we have covered that to some degree. But I want to start with, I want to skip those and leave those to biochem in terms of deeper conversations. And I want to talk to you about amino acids, proteins, and peptides. In part because, regardless of whether you go to Biochem 420 or Biochem 421, they expect you to know this stuff coming in. They expect you to know something about amino acids. They expect you to know something about the chemistry of water. They expect you to know acid-base chemistry. And so I want to cover this here and give you an opportunity to get familiar with amino acids. Now, if you look at your textbook, there is a table that has the quote-unquote naturally occurring amino acids listed. You need to know these. And like I said, when you go to biochem, you're going to be expected to know what the structure of valine is, serine, phenylalanine, and you're going to be expected to know how they behave, okay? So for example, if you look at glycine, what can you tell me about glycine? What's curious about it? It has a carboxylic acid, and it also has an amine. So we have an acid and a base together, don't we? So is it neutral, or is it zwitterionic? Well, it's a neutral amino acid in the sense that the side chain is non-ionizable. The side chain for glycine is just a hydrogen. There's just a hydrogen off the alpha carbon. But if you notice, the alpha carbons of each one of these are substituted with something that can't be ionized. It's just hydrocarbon kind of stuff. So at physiological pHs, they are neutral. But the amine and the acid, if I just throw that in water, will it be neutral or will it be charged? It'll be charged. Acids react with bases, right? And so we have this kind of situation where we have an acid and a base together. And this allows us to condense these things together and make polymers called proteins and peptides that are very useful biologically. So there's the name glycine, the abbreviation G or Gly. Again, in biochem, they're going to expect you to know that pretty quickly. That's just memorization. I will mention to you that I favor the 3-letter abbreviation as opposed to the 1-letter. And I favor it simply because I can remember it, okay? So on my exams, we're going to focus just on the 3-letter abbreviations. But notice when you get to biochem that they will expect you to be able to do both. Now, it's pretty simple. You know, Gly and then G, that makes sense, right? But if you get down to the tyrosine, T-Y-R and then Y, right? And so I've always wondered about that. But for the others, it makes sense. V for valine, A for alanine, so on and so forth, right? W for tryptophan? Well, obviously we can't use the first letter because tyrosine and tryptophan both have a T. But why did they pick Y? Why did they pick W? I have no clue, okay? So we just have to live with it, okay? I will tell you that biochemists favor the 1-letter abbreviation. Large part because they're dealing with large proteins and peptides, and single letters are a lot easier and a lot faster to write down than 3 letters, okay? But they mean the same thing. Notice here what we have. We have 4 values that you do not need to memorize, at least for my class, and nor do I think you'll need to memorize them for biochem, but you need to know what it means. So here we have pKa1, pKa2, pKa3, and pi. pKa1 is the pKa of the carboxylic acid. What can you tell me about the pKa's of these carboxylic acids? Are they identical or different? They are slightly different based on structure. they're all more or less kind of in the right ballpark, right? Somewhere around 2. Although for phenylalanine, we see that it's a 1.8, so it's below 2. But more or less, they're just slightly above 2, right? Meaning that they're acids, right? The lower the pKa value, the stronger the acid. The pKa of the amino group in its protonated state of the NH3, what can you tell me about these? They're all about 9.5 or so, right? Except with the exception of phenylalanine. It's a little high, a little lower. It's about 9.1. And for tyrosine as well. So we're all about that mid-9 region, okay? And then we've got this pKr group. Notice it's vacant for most of them with the exception of tyrosine. Tyrosine has an alcohol that can be ionized because this is really a what? What's that functional group? It's a phenol, and phenols are more, phenol's fine, are more acidic than a typical alcohol, right? And so what you see is that this OH has a pKa that we might expect. Phenol has a pKa of 10. This is slightly higher than 10 because there's an electron donating group on it, kind of what you would expect. Okay? Then we have this value called Pi. Anybody know what that means? Okay, it does have something to do with the whole molecule. It's kind of like an average, but not quite.
Well, it works for most of them, then you get down to tyrosine.
Average of what?
Average of all pKa.
All the pKas? 2 pKas? So yeah, if we look at glycine, 2.3 plus 9.6, what's that if we add them together? You divide by 2, we get 6, right? So what does Pi mean? If I'm averaging those 2 pKas, what physical value does that mean? That number in and of itself is totally meaningless unless you know what it means. What does it mean? Anybody? It's the isoelectric point. What does that mean? Let's do a little experiment. Let's see if we can figure out what it means. Because it's a very important thing that you all need to know something about. So let's suppose we have glycine. The structure of that's pretty simple. So we have glycine. And let's suppose we put it in a solution at low pH. Okay, so we put it in a solution at low pH. It now has what kind of charge associated with it? It's positively charged, right? It's a positively charged amino acid at low pH. So now let's suppose we take a paper strip and we wet it with a buffer that can conduct electricity, and we hook it up to a battery that has a positive pole and a negative pole on both ends of the paper strip. And we place this amino acid at low pH right in the middle of that paper strip. And so here's the battery. And we've got a little switch. Okay? Physics, that's right. I was an electrical apprentice for a while, actually, before when I was in college. So we throw the switch. What happens to the amino acid on the paper strip? It's going to migrate to the negative pole, right? Now let's suppose we take our glycine and we put it in a solution at high pH. Now it's what charge? Now it's negatively charged. So at high pH, how would it move? So at low pH and at high pH. It won't move at all at pH 6.0. That's exactly right. It's isoelectric. That's where it's in its zwitterionic form. So at pH 6, it is charged, but it is overall neutral. And so when I place it in, or on the strip, apply the field, it doesn't move. Does anybody know what this technique is called that I've just described here through this experiment? Well, there is a such thing as gel electrophoresis. The one I'm describing is actually paper electrophoresis, but electrophoresis is really what we're after, right? I think I'm spelling it right. So it's electrophoresis, and it allows us to separate things based on charge. Okay? You can separate amino acids, you can separate proteins, peptides, the whole 9 yards using, well, as Yusuf said, gel electrophoresis, which is the biochemist's best friend. Okay? It allows us to separate molecules based on their charge. Okay? Now, the system that I have shown here is essentially the system. Okay? Instead of using a battery, use a high dollar power supply that keeps the current constant and all that kind of stuff. But the principle is exactly the same. Now imagine that we do a different experiment. Okay? So, we use a special gel or paper strip that has a pH gradient through it. Meaning what? What would that mean? What is a pH gradient?
Like here, it's got pH 2 and then 3.
It means, yeah, we're moving, changing pH throughout. So let's say we go from pH going in this direction. So low pH to high pH. And then you can set on, in the middle of this, for example, you could put a mixture of amino acids that have different pIs. So what happens when I turn it on? So let's say I've got 4 amino acids, all have a different pI. What happens to those amino acids? They will migrate in either direction depending on their charge, right? But they will migrate until they reach their pI. So wherever that pH in that gradient or that gel is equal to their pI, then what happens? Why do they stop moving? Because then they're zwitterionic, and they're being tugged equally by the negative side and the positive side because they've got both charges, and they just don't move. So you can separate things based on pI using electrophoresis if you have a pH gradient in the gel. For those of you who are in biochemistry, this will be your main tool of choice. For those of you in molecular biology, this will be your main tool of choice. When you start doing things with large macromolecules, you will separate them on some type of gel using their electrophoretic mobility. And that's a fancy word for moving in an electric field. Okay? But this is this is the technique. And if you think about what we just saw in there for PI, how do we know it has to be the average? And what did we average? Actually, what we're doing is we're averaging the 2 pKa's that are closest to one another. Okay? And the reason that we're averaging those is because those are the ones that are going to be most likely to participate in the overall zwitterion formation, right? Now, let's think about this from first principles. Let's suppose we have a weak acid, HA, which we always like to pick on, right? Which doesn't exist. What happens when we place it in water? It partially dissociates, right? Into H plus and A minus. We're really talking about Gen Chem stuff here. How do we describe that process? No, how do we describe it mathematically? What quantity did you all use in Gen Chem? Say it. The Ka value, that's right. And we know that Ka is equal to what? Products over reactants, right? So the products are H plus, A minus, and the reactants are HA. And so if this is a stronger acid, the value of Ka is going to be large. If it's a weak acid, the value of Ka is going to be small, right? And so we're dealing with weak acids here, so the Kas are going to be small, right? But there's a way that we can rearrange this equation to where it's actually more useful for us. Anybody know what the name of that equation is? Hasselbalch equation, that's right. Can you derive it from that? Not probably. Absolutely. The Henderson-Hasselbalch equation is nothing more than the Ka equation rearranged algebraically. Okay, and it got a name associated with it. And it turns out that we could rearrange this so that we have Ka is equal to H plus over 1 times A minus over HA. Does everybody agree with that? Pretty straightforward math, right? And then this guy got his name associated with it just for doing some algebra, right? Now, it turns out that we don't like dealing with Ka, we like dealing with pKa, right? Because Ka, these are small numbers, you know, like 10 to the minus 5, 10. So we just take the pKa value, right? So if we, what does it mean to this is going to sound weird. What does it mean to p something? Take the negative log, right? So you can take the p of just about anything. So you take the negative log of both sides. And so the negative log of Ka is what? So pKa is equal to the negative log of H plus is what? pH, right? Minus the log of A minus over HA. And so I can rearrange this now to where pH is equal to pKa plus the log of A minus over HA. Just did a little algebra to get it to where pH is there. You all knew this as the buffer equation in Gen Chem, right? So what do we know about it? Okay. So when would that happen? Yeah, when the concentration of your anion and the concentration of your intact acid are equal, this becomes 1 and the log of 1 is 0. And at that point, we have pH equal pKa. Why am I telling you all this? Other than to throw back to general chemistry a little bit. Something to do with the Zwitterion? What else? Why is this important? What's on that table? A bunch of pKa values, right? How did they come up with those pKa values? They didn't come down on stone tablets, I can tell you that. Right? We had to figure out what they were. Well, how do you figure out what a pKa is? Use the Henderson-Hasselbalch equation. And you titrate them, right? And so what Sarah would do is she would take her glycine and she would put it in solution. She would add a little acid to make sure the pH is low. And we would start titrating it. Exactly like you did titrations in Gen Chem. The burette, right? So we have this solution that would actually have this because we're doing it at low pH to start with. And she would have a pH meter in there. So she could measure the pH of the solution because it's water. And she would have a burette filled with what? What would we titrate it? Base? What base would we use? Sodium hydroxide. And we would start to add sodium hydroxide little bit at a time. So on the y-axis, we would have pH. On the x-axis, we would have volume of base. Right? And so we're starting off at really low pH. We're here, we haven't added any base yet. And so what happens as we start to add base? pH goes up, like that. There's a buffer zone. There's an equilibrium, and you all are making a shape, right? And you're all making the right shape. What is the shape? It's kind of S-shaped, right? An S-curve, right? Sigmoidal. So as we start to add a little bit of base, the pH starts to go up, but does it go up dramatically? Kind of goes off, you know, like that. And then when we get to kind of where we're starting to completely titrate all of this, because this is the acidic component, right? What happens? Then it rises really sharply, right? So we will kind of go and it rises sharply, and then it starts to level off again, right? So we've titrated all of this at that point, right here, right? So that's the first equivalence point. And what would we have at that point? We would have that species, right? We've titrated the acidic component first. Now we're titrating the next most acidic component, and you see that it kind of levels off again, and then we get another spike. And at this point, what do we have? We would have that species. Way down here, what species do we have? We have this species. That's a 3. Now, how do I use that data to get the pKa values? I see the equivalence points, but how do I know the pKa values from this? How do I use the equation? I mean, I got a graph, right? How do I take stuff from a graph and put it into an equation? Conceptually. Okay, so I've got pH, right? Whatever that pH might be. Now, if we're looking for the pKa, we got to find the point where these are equal, right? So where would this and this be equal? This is A minus of that, right? It'd be halfway between here and here, right? So you set up Excel and you find the halfway point, and you just extrapolate, right? So you know that you had 0, and you added so much volume here, you simply take the midpoint. And at that point, you know you have equal concentrations of this and this. That cancels out, so I know that the pH, whatever the pH value is there, has to be equal to the pKa, right? Now, this is our new HA, and this is our new A minus. And so we would take the point here and take the average, and that would be pKa too. We can do this all graphically. And you can actually set up Excel to take the data points and actually spit this stuff out for you immediately. And you can actually even use a little calculus, if you've had calculus, right? Because how do you find this point accurately? Is it just halfway between here? It's actually the point at which the derivative is at a maximum. And so you can actually do a little calculus. You can actually sit there and solve a derivative, okay? It's actually quite easy to do. Because the way that we teach you to do derivatives and stuff in mathematics is not how chemists do derivatives at all. We actually do approximations and stick things into Excel, and it gives us numbers that are accurate enough. Okay? This equation right here, when you get to biochem, will be the equation that haunts you the most. because from that simple equation, you can determine the overall charge on a protein. You can determine the overall charge on a peptide, and not just an amino acid. And it turns out that's very, very important for modeling proteins and how they're going to move within an electric field. Fortunately, there's all kinds of calculators on the internet now where you just enter in the sequence and it'll give you the PI value for it. But it uses this equation. Okay? It's just now all of a sudden you have maybe 1,000 amino acids that you have to take into account using that equation. Okay? But it's nonetheless that equation. So I want you to know what you learned in general chemistry. Very, very important when you get into upper level organic and into biological systems. Very simple concept. You all did all kinds of titrations. We can derive a lot of valuable information from those titrations. And of course, now you can simply look up the values in your book, right? So, glycine has no R group. It's just 2 hydrogens on the alpha carbon. Is it chiral or achiral? It is achiral. It is the achiral amino acid in the natural series. Every other amino acid beyond that is at least 1 chiral center. All of these are L amino acids, meaning what? Are they R or S? All of the natural L amino acids are S, with the exception of cysteine, which is R. But it's still an L amino acid. Does anybody know why it changes from R to S? It has to do with how we assign priorities, right? When we get to cysteine in a minute, you'll see why it changes, okay? So alanine is just a methyl group placed on glycine. So one of the hydrogens has a methyl group now. Valine has an isopropyl group. It's always, everybody always remembers valine because that just looks like a V. Pretty straightforward, right? Lysine is like a V with a methylene in between. Lysine and isoleucine, okay? That's a little confusing, but this is the isomer of leucine. We've moved the methyl group over here, and now we have how many chiral centers? Now we have 2 chiral centers, and it turns out that in the side chain it is also of the S configuration. For some reason, it turns out that nature really likes the S enantiomer. I don't know why, but interesting. In a lot of cases, you'll find the S enantiomer in drugs, proteins, peptides, and usually you find out that the R enantiomer, especially in drugs, not always, but quite frequently, is actually toxic for a variety of reasons. Phenylalanine is pretty easy to remember. It's got a phenyl group, right? It's an aromatic side chain. Tyrosine has a phenol. Tryptophan, this group here. What do you all know about tryptophan? Turkey, right? It does not. There are. The stuff about tryptophan and all that stuff you hear about making you sleepy is utter nonsense. It really is. Because if that were true, cheese would make you tired, because cheese, by weight, has more tryptophan in it than turkey does.
So are people just eating too much and getting tired?
That's exactly what's happening, right? It's Thanksgiving. You got a big turkey. You've just eaten. The football game's on. You're in your recliner, and you fall asleep, right? That happens to me whether I eat turkey or not, okay? So tryptophan doesn't really do that kind of stuff. That's nonsense. Serine, okay, has an alcohol, a primary alcohol in its side chain, okay? So in all of these, you pretty much so see some type of methylene between the alpha carbon and whatever the side group is, okay? And so you can kind of remember it that way. So you can think of alanine and then something added on the end of that to make the others, if you want to think of it that way, okay? But these are what we call the neutral amino acids because these side chains are fairly hydrophobic. So if you were going to make a protein, and proteins can take on shapes that we'll talk about, would these amino acids most likely be on the inside of the protein or exposed to the water? These amino acids. With the hydrophobic groups? They want to go away from the water, so they kind of form on the inside, okay? And so they form on the inside. Whereas serine, it can form hydrogen bonds. You'll typically find it on the outside of a protein, okay? Now you can find some of them on the inside too, but I'm just saying in general, right, we're following our hydrogen bonding rules that we've learned about. Okay, so that's the neutral amino acids. We have others, right, because it's continued here, right? Threonine, what kind of alcohol is that? It's a secondary alcohol, so you can think of it as a serine analog, if you will, with an extra methyl group. Prolene is a very special case. What's so special about prolene compared to the other ones? What functional group? Here? What kind of amine is that? It's a secondary. What are the others? They're all primaries, aren't they? Prolene is a privileged amino acid, and it has a lot of interesting consequences when you put that into a protein. It actually breaks helices. So we'll talk about alpha helices on Wednesday, but it turns out that Prolene can actually break those alpha helices quite well. Again, we've got all the numbers that you all can focus on later because we've already talked about that. Don't worry so much about hydroxyproline. It's a fairly rare amino acid. Cysteine is just like serine, right, except the OH is replaced with SH. It's a thiol, right? And like I said, serine has the S stereochemistry here, but cysteine has the R stereochemistry. Why is that? Even though they're both L. Notice the side chain is off to the side just like it is here. The amine's coming out towards us just like it is here. So why is the stereochemistry here different? Sulfur has a higher priority, and so because the CIP rules dictate R and S, right, this actually has the R stereochemistry. Okay? Now the special thing about cysteine is that sulfurs, or these thiols, will oxidize and form these disulfide bridges. This is really just two cysteines put together, but we call it cysteine, or cysteine-cysteine linkage, and that turns out to be very important, ladies, for your hair if you go and have permanents. Right? They actually are reforming your disulfide bonds to change the structure of your hair, and we'll talk more about that on Wednesday. Then we have methionine, which is another sulfur-containing amino acid, but it has, instead of a thiol, what is this functional group? This is a thiol. This is so we have a methyl group, sulfur, and then a methylene. What is that? It's kind of like a sulfur version of an ether. And what do we call those? Sulfides. That's right. So this is a sulfide. And then here we have asparagine, which has an amide. What kind of amide is that? That's a primary amide. And then we have glutamine, which also is a primary amide. But notice there's another methylene in between the alpha carbon and the primary amide. My favorite amino acid? Do I have a favorite amino acid? We've been doing a lot of work with unnatural amino acids in my lab, and we've been doing a lot of work with an unnatural version of cysteine, where we've replaced the alpha hydrogen with a methyl group for various reasons. We could talk about that later if you're interested in it. But we do a lot of synthesis of unnatural amino acids in my lab, which is another reason why I like this chapter. So something a little closer to what I like to do. Now there are amino acids that actually have side chains that are ionizable. Right? So if you look at aspartic acid, you've got the alpha carboxylic acid, because it's attached to the alpha carbon. You've got the alpha amine, but then you've got this other carboxylic acid group. Okay? Now notice the pi. What values did they average to get that pi? The two closest ones. You actually average the two carboxylic acid values to get the pi, not the amine. Because this is going to be positively charged. And then you've got to figure out the average of these so that you can get the pi. Okay? So there's aspartic acid. There's glutamic acid, right? And so if you look at aspartic acid, asparagine, you can see similarities. It's just an amide versus a carboxylic acid. If you look at glutamine, it's an amide, and glutamic acid is an acid. So they're kind of related in a lot of respects, right? So you can imagine actually making aspartic acid from asparagine just simply by hydrolyzing the amide to the carboxylic acid. Okay, so a lot of relations in a lot of these. And so here we also run into some issues, right? Aspartic acid, ASP. Alanine also has an A, so it's a D for aspartic acid. And I always have trouble remembering that, okay? Glutamic acid, right? Glu, G, same as glycine. So they call this one E. I don't know why, right? Now this is the one that always confused me when I got into biochem when I was an undergraduate, because I was looking at these structures very naively, and I kept going, why in the world is there potassium in proteins, right? K is potassium, right? It's on the periodic table. But to a biochemist, K is lysine, right? Can't use L because there's also leucine, so they use K. Why? I have no idea. Again, actually, lysine is probably one of my favorite amino acids. It is an essential amino acid. What does that mean, essential? It's right. We can't synthesize it. So if we can't get this from our diet, we're in trouble, right? And so got to be able to acquire this. Oh, yeah, other animals synthesize it. I mean, just not us. That's why we have to eat those things. No, it's okay. It's all right. Arginine, this one is really easy to remember. It's kind of the pirate's amino acid. Arginine, yeah, R. And that makes some sense, right? Arginine, R, I kind of get that one. And then histidine is another one as well, right? And that's easy because H and his, right? So those amino acids, you need to know the structure for the exam. You need to know how to figure out what their PI values are. You need to be able to sketch a titration curve for these various amino acids if I was to give them to you. All that stuff you need to be able to do. And you need to be able to apply the Henderson-Hasselbalch equation to determine the A minus to HA ratio. Huh? These are all of them that we're going to focus on. Yeah. Now, I told you not to focus on the hydroxyproline, so forget about that one. Okay, that's kind of a rare one that we're just not going to consider here. Not that it's not important, okay, but we're not going to be terribly interested in it. Okay? Let's go back. What do y'all know about phenylalanine? As a phenyl group? It is essential. What else do you know about it? There's actually a lot of essential ones, right? Things that we can't make. We can't make valine. We can't make leucine. We can't make isoleucine. We can't seem to make phenylalanine. We can make tyrosine. Maybe there's an enzyme that takes phenylalanine, right, and puts an oxygen on it through some type of electrophilic aromatic substitution reaction or something like that. Maybe we could do something like that, right? Tryptophan, we've got to get it in our diet somehow, right? But we can make some of these others. We make alanine, glycine, serine. They're not essential. How many of you drink Diet Coke at all? Aspartame, yeah. Aspartame. Read the back of the can one day. It says contains phenylalanine. And it's because aspartame has a phenylalanine residue. Why would they give that to you as a warning? Yeah, it's a pretty mild carcinogen. They don't warn you for things that are more carcinogenic than aspartame. That's right. There are people that suffer from phenylketonuria, meaning you don't have the enzymes to properly process phenylalanine. And if you ingest a lot of aspartame, which will degrade into phenylalanine, it'll make you sick. And so it's a warning label for people who may have phenylketonuria. Now, I don't know what the percentage of people that have that particular mutation are, but it's enough that Coca-Cola and the other soft drink companies using aspartame have to put that on as a warning label. With what? I don't know. People are worried about it because it actually has a methyl ester, and methyl esters saponify into a carboxylic acid, and what would be the alcohol if it's a methyl ester? Methanol. Right. And methanol gets oxidized by your liver to formaldehyde, which pickles you, pretty much, right? Now, the thing is that it turns out you really don't have to worry about this too much, because it turns out that the human body does not have enzymes that process methyl esters. We have enzymes that can process esters like triglycerides, and we have esterases that can actually process ethyl esters, but for whatever reason we don't seem to have enzymes that can process methyl esters. So the only way it could hydrolyze would be in the acidic environment of your stomach, and it doesn't stay there very long to actually undergo hydrolysis, so it can pretty much pass unmetabolized. So that's pretty convenient. So you all need to figure out whatever works for you, a good system to know the structures of what these amino acids are, and remember how to calculate the various pieces. Now I want to spend a little bit of time handing some stuff back and then working a couple of problems. So on this one, some of you turned them in together, so I'm just going to hand to whoever's the first name on the sheet. Ian, he's not here, so Dane. Megan. Coates. Molly. Caroline. Thomas. John. Olivia. Jordan. Grace. Dane. Ian's not here. Megan. Autumn. Molly. Sarah. Caroline. Coates. Thomas. Gauntz. Yusuf. Gabriella. John Michael. All right, let's look at this real quick. We don't have a whole lot of time, but we'll go over a couple of problems. So if you look at problem 3, we had to make this from the acetoacetic ester synthesis. Some of you started let's see, 1, 2, 3. That's a bad box, but there it is. Some of you started with that. That's not sufficient. That is an intermediate that you need, but you need to tell me how you got that. Because the acetoacetic ester synthesis starts with this. And that's by definition in its name. So you had to have that 1,3-dibromo or dichloro propane generate the enolate, that then double alkylates, and then you proceeded from there. So I gave partial credit for that. But you have to start from this because the acetoacetic ester synthesis dictates that you start with that. Question 5, the multi-step one. We had some issues going on. So we're starting with the benzaldehyde. And the first thing that we did was reacted it with a Wittig reagent. And so what are we going to do there? What's the Wittig reagent going to do? We're going to make a carbon-carbon double bond. Most of us got that. However, there were a couple of cases where we lost a carbon there somehow. So if I circled that, that's what that means. You, for whatever reason, put in one carbon too few. The second step then was to use diphenyl copper lithium. What's that going to do? It's going to add a phenyl group. In what way? 1,2 or 1,4? 1,4 because it's a cuprate, right? So it's going to do Michael chemistry here. And when we do that, you get this in solution. What is that? Right? If the phenyl attacks here, right, we have to move the electrons, and that's an enolate. And then what I said was it was followed by what? Not followed by dibol. Methyl iodide. This is the part that surprised me. Many of you wanted to make that a proton donor so that you added a hydrogen. That's what would happen if we just dumped it into water, right? But what happens here is just an SN2 reaction on an enolate to make a new carbon-carbon bond. So there we were showing that we could form an enolate by conjugate addition, making an important carbon-carbon bond. But then we could also make a second carbon-carbon bond quite easily by, instead of dumping it into water, dumping it into a different electrophile. And so that gave the product from that step. Right? And then we did dibol, which does what? Dibol at minus 78. What can it do to esters? What does dibol do to an ester at low temperature? To what? Reduces it to an aldehyde. So then we have that. And then here, C6H11 magnesium bromide. Many of you put phenyl magnesium bromide. C6H11 can't be a benzene ring, right? But it's what? It's a cyclohexane ring. So I've marked on that. Not, if you put phenyl magnesium bromide, I circled it and wrote not a reagent given, and then I went up and kind of circled up there that you needed to look at that, okay? So you need to know what these reagents are. And then so that simply adds to the aldehyde, right? After workup. You get a cyclohexane ring attached there. Does that make sense? All right, we're going to finish up our amino acid stuff on Wednesday. I want you to finish reading that chapter, okay? Look it over really well. We're going to have about, it's going to be quite a period of slides, okay? And the slides that I'm using are not from the book. So they're available on Blackboard. Make sure you take a look at them. It's a simpler set of slides than what comes with the book, because I really want you to understand this stuff at a fundamental level, not necessarily a higher functioning level, because you're going to get that when you get into biochem, okay? But I want you to be really prepared for the things that they expect you to know when you get into 420 or 421. All right, have a good afternoon. See you on Wednesday.